This is lecture 26 on urban transportation planning. We will continue our discussion on trip distribution analysis and try to complete the discussion on this topic in this class. To have a continuity of discussion, let us try to recapitulate what we did in the previous class very briefly. You may remember, after completion of our discussion on doubly constrained gravity model, we discussed about growth factor methods of trip distribution. Even though these methods are very old methods and very simple with their own associated problems, still these methods have some relevance even in today's context. That is the reason why we started our discussion on growth factor methods. We discussed about two basic methods. Number one, uniform factor method, and number two, average factor method. Let us check ourselves now whether we have captured the relevant points about these two methods, namely uniform factor method and average factor method. To recapitulate the previous lecture, namely lecture 25, the first question to you is this: what is the input data required for growth factor methods of trip distribution in general? Input data required for growth factor methods, it could be uniform factor method or average factor method. Any response, anybody? Just the input required for this method.
Number of trip attractions and number of trip productions should be the input for the growth factor method.
It is different. Actually, trip productions and trip attractions are inputs for the earlier methods that we discussed, the synthetic models, namely gravity model for trip distribution. Whereas here we need the base year trip distribution matrix itself as input data. We need to collect detailed data on origin destination information and prepare a matrix, and that is the input data for growth factor methods of trip distribution. So input is very elaborate, and we try to manipulate the matrix to get the horizon year matrix, right. The next question: what is the basis for uniform factor method of trip distribution? What is the assumption that we make in this method? As the name implies, we assume uniform growth for the whole of the urban area, uniform growth rate for each of the traffic zones in the urban area is the basis. Based on this assumption only, we work on uniform factor method of trip distribution. Third and last question: how is average growth factor method different from uniform growth factor method? What is the difference? Any volunteer? Difference between uniform factor method of trip distribution and average growth factor method of trip distribution. As their names imply, in the case of uniform growth factor method, we assume or we consider a single growth factor for all the traffic zones. There is no variation at all. Whereas in the average growth factor method, we recognize the fact that there could be different growth factors for different traffic zones, and we consider a zonal pair and take the average of the growth factors of the two zones involved in a zonal pair, right. So that is how the average factor method is different from uniform factor method. Clear? Now with this understanding, let us proceed further to discuss about other growth factor methods that are available for application today. The third method is Fratter's growth factor method, named after the proposer of this method. This method was introduced by T. J. Fratter in the year 1954, very old but still valid even today for specific situations. According to this method, the total trips of each zone are distributed to the interzonal movements as a first approximation according to the relative attractiveness of each movement. See, the trips at a zone will be attracted by different zones based on their ability to attract trips. So, relative attractiveness is the basis for distribution of trips as per Fratter's method. To add more information about this method, we can say that the future trips estimated for any zone, or the horizon year trips that we estimate for any traffic zone, would be distributed to the movements involving that zone under consideration in proportion to the existing trips between it and each other zone. That will be known to us, because we will know how the trips are being distributed in the base year from one zone to all other zones. So, that is what is stated here, and to the expected growth of each other zone. Maybe we can just give the same information in a mathematical form which can be understood easily. This may be expressed mathematically as follows: Tij is equal to small Tij Qi by small Qi, Qj by small Qj into sigma j1 to n small Tij whole divided by sigma j equal to 1 to n Qj by small qj multiplied by Tij, where the notations are as follows. Capital Tij is nothing but future trips between zones I and j, the horizon year trips that we want to know, and Tij or small Tij is a present trips between zones I and j which is known to us. This information is available to us. Qi future trip ends at zone I. Should we have this information with us before distribution or not? Capital Qi, we will have this information with us, because we would have completed the first two steps of the planning analysis, namely trip generation and model split. So, at the end of trip generation analysis, you will know the value of Qi for horizon year condition 2, is not it? You will calibrate the model for base year condition and use the model to predict the trip production of each of the zones for horizon year condition. So, this value will be known to us before we do trip distribution for horizon year condition. Qi is known to us, and small Qi is a present trip ends at zone I. Obviously, it is known, we collect data on Qi, is not it? And Qj future trip ends at zone j, that is also known to us by the prediction process, trip attractions. And Qj present trip ends at zone j, that is known to us through data collection process for base year condition. And n is the total number of zones in the urban area. Clear? Are you able to understand the logic of distribution of small Tij based on Qi, Qj and then the ratio of Taj for the base year and Taj for the horizon year. The denominator is nothing but Taj values for horizon year condition. We multiply Taj for each zone by the factor capital Qij by small qij, is not it. So, that is how the distribution of trips for horizon year condition is obtained as per Fratter's method. We will take a simple numerical example and see how Fratter's method can be applied, and of course before that we need to know a few aspects related to the application of this method. When the future traffic into and out of the zones is similarly distributed, each interzonal trip would have been assigned 2 values. For example, if you have zones 1 and 2 in the zonal pair, we will have T12 and T21, that is what is meant here by 2 values. One the result of the distribution from one of the zones involved and the other the result of the distribution for the other zone. To attain the base year symmetry, what is base year symmetry? Fratter proposed a symmetrical trip interchanges based on practical considerations. He has proposed T12 to be equal to same as T21, balancing trip interchanges. As a first approximation, those pairs of values are averaged. A new growth factor for each zone is then calculated and the distribution process is repeated. This is the example taken from the original work of Fratter himself. This was published by him in 1954 in a journal. These numbers are the same numbers as used by him. Okay. It is just an illustrative example, that is why the zone numbers are just given as A, B, C, D. Normally it is 1, 2, 3, he has just taken it as an example giving zone numbers as A, B, C, D, just 4 zones. And please note that this is OD matrix, origin destination matrix. So, one zone to other zone, it is not total trip interchange, it is specific to an origin zone and destination zone. You can see as per the data, trips from A to B is same as the trips from B to A, it is 10 in both the cases. Similarly, trips from B to C are same as trips from C to B. So, that is what is meant by the symmetry proposed by Fratter. And the sum of the cell values along a row are given in this column. First row sum 40 implies total trip production of zone A is 40 trips, is not it. PA is 40 and PB is 38, PC is 32 and PD is 38. And similarly, total trip attractions are nothing but cell values, sum of the cell values along columns, and we find the values are 40 for A, 38 for B, 32 for C and 38 for D. And since we have these values with us, the future trip productions and attractions for each of the zones, these numbers can be given straight away because it is the available data before we go for distribution of trips. So, that is what is given here 80, 114, 48, 38, again 80, 114, 48, 38 because it is symmetrical as per Fratter's proposition, right. Now, since you know the current as well as future trip totals in the form of productions and attractions, you can get the growth factors. or instead of productions and attractions we can say origins and destinations, because we deal with OD matrix. Okay. So, the growth factors are 2, 3, 1.5 and 1, here also 2, 3, 1.5 and 1. So, this calculation can be done based on the available data, clear. Base year trip interchange is known to us, origin destination information is known to us, and base year trip production or trip origins and trip destinations are known to us for each of the zones, that is what we have written here, and we predict the trip origins and trip destination for the horizon year also using trip production model. So, we get these numbers also readily available before we do the trip distribution process. So, using these numbers we get the growth factor values. What is the next step? Using the growth factors we are going to change the cell values of the matrix. We are going to extrapolate or enhance the values of the cells of the matrix, that is what we are going to do. We simply will manipulate the cell values of the given matrix, clear, and for that only we just follow the formula given by Frater. So, if you want to get the horizon year cell value for A B, we just calculate T A B to be equal to small t A B into Q A by Q A, is not it, factor corresponding to the origin zone, and Q B by small q b, the growth factor corresponding to the destination zone, is not it, and T A B plus T A C plus T A D or the trips originating from zone A to all the other zones, and T A B into A E B is nothing but trips that would be originating from zone A in the horizon year as per the anticipated growth factor, which is E B, right. We multiply the trip interchange by the growth factor corresponding to the destination zone, T A B multiplied by E B, not E A, okay, plus T A C into E C plus T A D into E D. Substitute all the values, all these values are known to us. T A B is nothing but the cell value in the available matrix, Q A is nothing but the row total, and Q A is also known to us, is not it, row totals for base year as well as horizon year is known to us, and in fact we have got the ratio also directly, Q A by Q A is available to us in the form of growth factor. So, we can take those numbers directly, and these values are known, and these values are to be multiplied by the corresponding growth factors, that is what we have to do. And so, you can substitute the values 10 into 2 into 3 whole divided by 40 is directly available from the matrix, so row sum divided by the corresponding values multiplied by the respective growth factors, and the T A B value for horizon year condition is 36.4. On the same lines you can get the values of T A C and T A D, all the trips related to zone A, right, trips originating from A to B, A to C and A to D, and this part is same because we deal with zone A. So, obviously we can directly take these numbers as 40 by 66, that is what I have done here, only these values will change, and put the corresponding values and get the numbers as 21.8. In the second case also we get exactly 21.8, that clear. On the same lines you just calculate the other trip interchanges, T B A, substitute the corresponding values and we get 41.5 as T B A, and other trips emanating from B, T B C and T B D are 43.5 and 29.0. Then T C A will be 16 TCB 28 TCD 4, DA 15.8, DB 18.3, DC 3.9. Now, we are ready to put all the calculated values together. We have two values related to zones A and B. AB is 36.4, BA is 41.5. Similarly, for AC we have 21.8, CA 16.0, AD 21.8, DA 15.8, BC 43.5, CB 28.0, BD 29.0, DB 18.3, CD 4, DC 3.9. Please remember, initially we have been given a data which adhere to the symmetry condition. AB is equal to BA, right, AC is equal to CA. So, that has to be maintained. For that, we need to simply have only one value for both AB and BA as well as AC and CA and so on. The simple method is add up and get the average numbers, average values, and take this as a common value both for AB as well as BA, this as a single value for AC and CD to proceed with the next iteration, right. The averages of the trip interchanges between the zones are given in a matrix form below to determine the new growth factors. Put these numbers and develop the trip distribution matrix, and this is the matrix you will be getting. You can see the average numbers that we obtained earlier are given as cell values 39, 39, 18.9, 18.9, 35.7, 35.7 and so on. Symmetry is maintained. Then add up, these are the calculated trip destinations and calculated trip origins as per the first iteration, and then future values are fixed, already known to us, those values are there. Then based on the calculated trip origin values and destination values, arrive at the corresponding growth factors, right. You get 80 by 76.7 as 1.04 and so on, 1.16, 0.82, 0.82, similarly we get the same numbers on the other side because we maintain the symmetry. That is how these growth factors are same on both sides. Now take these growth factors and proceed with the subsequent iterations. The process is then repeated to obtain a second approximation on the same lines as we have seen earlier, but using the new growth factors and new values of interzonal movements, new values of the cells, right, obtained from the first approximation. The iterative process is continued until the values of the growth factors of the involved zones obtained based on calculations become unity. Once it becomes unity, your calculated and projected or predicted values are same, that is what you want. After distribution, the row totals and column totals of the cell values should match your predicted trip origin totals and trip destination totals, right. That will be satisfied once you get the growth factor value to be unity. Okay. I strongly advise all of you to continue this exercise and reach the point of convergence where the growth factors reach unity, and check whether you are able to get the expected matrix for the horizon condition. This is about Fratter's method of trip distribution, and after Fratter, a person named Furness suggested a similar method, but relatively simpler in the analytical procedure. The method devised by K.P. Furness in 1965 is also iterative in nature. For this, the estimate of the future traffic originating and terminating at each zone are required, thus yielding origin growth factors and destination growth factors for each zone. I am just reading out the background information as given the literature. It is nothing different from the input required for Fratter's method, the same information about the origin, okay, related to trip origin and trip destinations. Okay. It is nothing different from the previous method as far as the input data is concerned. The traffic movements are made to agree alternately with the future traffic originating in each zone and the estimated future traffic terminating in each zone until both these conditions are stratified. Please remember, the term traffic is used in the original literature. I am just repeating the same thing. If you can understand this as future trips or involved traffic, both are same. The word traffic can be replaced by trips as far as this explanation is concerned, nothing different, because we are dealing with only person trips, not vehicular traffic. Okay. The term traffic here means only person traffic. We will straight away take an example and see how Furness method is applied for distributing horizon air trips. This is the example. Origin and destination information pertaining to 4 traffic zones are given here, and please note that the symmetry constraint is not introduced here. For example, number of trips originating at zone 1 and destined to zone 2 or 3, and number of trips originating at 2 and destined to 1 or 6. So 1 2 is different from 2 1. So that constraint is not introduced in this particular case. It is just open situation. You can deal with any kind of origin destination information as per Furness method. Okay. And total present trips are given here, as well as the total for the rows are given here. The totals are totally different from one another because there is no symmetry condition introduced in this particular case, and this information will also be known to us. The horizon air trip origins and trip destination zone wise would have been already calculated by us using trip generation model. Then using these totals, you calculate the destination growth factor and origin growth factors, one divided by the other. The values are as given here: 1.5, 1, 2 and 3, 3.5, 1.5, 1.1 and 1.2. They are also not maintaining any symmetry. Clear? The same step is explained in the form of statements here. The matrix gives the details of base year trip distribution. From the values of the predicted future trip origins and destinations, the origin growth factors and destination growth factors are calculated for each zone, isn't it? That is what we have seen. And each column of the matrix is then scaled by the appropriate destination growth factor, such that the column totals become equal to the predicted column totals. Then the result will be as follows. What is meant by this statement? Each column of the matrix when they say each column of the matrix, they mean each of the cell values in a column, each of the cell values in the column. When they say each column, each of the 4 cell values in a column, okay, is then scaled by the appropriate destination growth factor. We saw the destination growth factors are given at the end of each column. If you want, I will just go back. So, this is the given data. So, these growth factors are destination growth factors, these are origin growth factors, right. By the statement that we have just now seen, what is meant is this: we multiply each column, right, by the corresponding destination growth factor first, or in other words, each of the cell values in a column is multiplied by the corresponding destination growth factor. We are going to multiply 8 by 1.5, 6 by 1.5, 10 by 1.5, 2 also by 1.5. Then 3 will be multiplied by 1, 9 again by 1, 8 by 1, 4 by 1, right. So, this is a process that we actually mean by this statement. Each column of the matrix is then scaling up based on the growth factor by the appropriate destination growth factor, such that the column totals become equal to the predicted column totals. Obviously, when you multiply by the corresponding growth factor, you will find that the totals are matching with your predicted totals. Then the result will be as follows. Let us see how we get the result after this particular step. Since we have just scaled the columns using the growth factors, we find interestingly the calculated totals as per after scaling up are these values 39, 24, 68 and 120, and the predicted destination values are the same, right. And because of this scaling up, there is change in the cell value, and if we total up these cell values along rows, we are getting totals like this: 92, 49, 53, 57 and so on, and the predicted values for each of these zones along the rows are 147, 42, 32 and 30. They are obviously different from the predicted values, right. So, calculate new growth factor based on the required desired values or your own predicted values and the calculated values, right. 147 by 92 for example gives you 1.6. Do the same calculation for other rows, you are getting 0.86, 0.6 and 0.5 as growth factors for origin zones. What is the growth factor for the destination values? It is already 1, right, and continue the exercise. Now, by scaling the rows with the corresponding growth factors, right. However, it can be seen that this has resulted in the calculated row totals of cell values not tallying with the predicted totals, that is what we have seen, and hence a new set of origin growth factors is now computed for each zone by dividing the predicted trip total by the total obtained by the for the row by the column scaling mentioned earlier, and in the next step each row is scaled up by the new growth factor giving correct row totals. This however disturbs the column totals. Obviously, when you try to tally the row totals, the column totals will get disturbed. As before, new destination growth factors are computed for each zone by dividing the predicted trip total by the total obtained by the row scaling. Are you able to understand the iterative procedure? First you scale up based on destination growth factor and the origin growth factors or origin cell values get disturbed, origin totals. So calculate growth factor, use those factors to scale up the cell values along each row. Now we will find along each column there is disturbance, then work out new growth factors along for each column and use those factors to scale up the cell values, and there will be disturbance along row, and continue the process until there is a match, until there is no disturbance along columns as well as rows. So analytically you find that the procedure is quite simple compared to the procedure proposed by Flatter. He is involving a big analytical procedure involving the current trip interchanges, then growth factors for origin destination zones, and then ratio of the trip interchanges for the base year and horizon year and so on. All these things are not here, simply only one simple calculation is involved here, namely scaling up the cell values using the growth factors for columns first and then for rows, and repeating the procedure until you get the growth factors to be almost unity, so that there is no disturbance of the cell values of the matrix. And just to show you the result of this exercise, you can see the result here. After scaling up using origin growth factor, you find that the calculated values of origins for each of the zones are shown here. They are nearly equal to the predicted values or desired values, 147.2 instead of 147. You can take it as round it off to 147 itself, and this can be rounded off to 42, the desired value is 42, and this can be rounded off to 32 and desired value is also 32. You can round it off this to 30, desired value is 30, it is exactly matching, whereas here there is a difference between the calculated totals and the desired values. We have 37.53 instead of 39, 19.46 instead of 24, 75.98 instead of 68, and 118.38 instead of 120. So work out the new growth factors for the columns. We get 1.04, 1.23, 0.89, 1.01, much better. They are relatively closer to unity compared to the previous iteration, right. Use these growth factors, scale up the cell values along each column using these factors and get the resultant matrix, and you will see that there is some disturbance in the column totals, and repeat the procedure until there is no disturbance at all in your cell values, and you get growth factors to be nearly unity. The columns are now scaled again using the new destination growth factors, and this iterative procedure is repeated until all growth factors or unity or sufficiently near to unity. This indicates to you that it may be very rare that you get exactly one as growth factor for all the trip origins and trip destinations. That is why you must go on iteratively doing the exercise and identifying the point of convergence until all growth factors are unity or sufficiently near to unity for the user to feel satisfied. That is more important, your satisfaction is more important, and confident that he or she has obtained the desired degree of accuracy. Desired degree of accuracy, accuracy is left to your desire. You fix a level of accuracy and try to attain that level by the iterative process. Is that clear? Right. And this is the final statement regarding furnace method. Furnace method gives results similar to Fratter's method, same result, but requires relatively less computations. That is the advantage of furnace method. So, Fratter proposed a method in 1954. After 11 years he has come out with a method which is relatively simpler in terms of analysis, but still gives you the same result. Okay. And in practice people make use of both the methods, I would say. Some planners make use of Fratter's method even today because of the fact that Fratter's method goes in detail about the present trip interchanges and predicted trip interchanges also. The formula takes care of those variations, whereas furnace method relies on mainly scaling up the cell values based on the growth factors. It is not relying much on the trip interchange values for every iteration. Okay. Right. This completes our discussion on the different growth factor methods available for trip distribution. Now let us try to look at the disadvantages as well as advantages of growth factor methods. Disadvantages of growth factor methods of trip distribution, or you can say call it as a limitation. Okay. The first disadvantage is this: these methods underestimate movements where present day development is limited and overestimate where present day development is intensive. What do you understand by this statement? Let us say there is a large number of trip interchange between a particular zonal pair for base year condition because both the zones have fully developed, and by growth factor methods we just extrapolate or manipulate the cell values which are reflection of trip interchanges for base year condition to get horizon year values. This implies that when you have a higher value of trip interchange between a zonal pair, your horizon year trip interchange is also going to be proportionate to your base year trip interchange. In another case, zones would not have developed that much under base year condition, but might have potential for faster development later after 5 or 10 years. The current trip interchanges may be relatively less, but you are going to assume that even the horizon year condition for such zonal pairs the trip interchanges are going to be relatively less. It may not be true. The zones might grow faster and the interchanges may be quite different from the base year trip interchanges. So this possibility or this kind of possible changes are not taken into account in the growth factor method because we are simply manipulating with the base year matrix. The extreme case is this: if the present trips between any two zones is 0, it is possible trip interchanges between a set of zonal pairs become 0 between zone 1 and zone 200, which are quite far away, might be 0 for base year condition. As per the growth factor methods, the future trips also will become 0 because of the base year value being 0, because the base year value is 0, right. So this is the extreme situation. We are simply trying to reflect the base year condition by growth factor methods. And then these methods do not take into account the resistance to travel between zones, which is an important factor, and thus imply that the resistance to travel will remain constant. There is no Fij involved in the trip distribution using growth factors. Fij is a very important factor reflecting the resistance to travel in the form of travel time, travel cost and other associated benefits and disbenefits. So that factor is not at all brought into the picture in growth factor methods. We simply ignore the travel resistance. Once we ignore the travel resistance, it implies that we assume that the travel resistance is going to remain unchanged between base year condition and horizon year condition, isn't it? For base year condition, whatever cell values you have in the matrix, base year matrix, is obviously reflective of the travel resistance, because people have actually exchanged trips. The cell values for base year condition reflect Fij values accepted, but the Fij between zonal pairs need not remain the same for horizon year condition. Traffic conditions might change, isn't it? In that case there will be change in Fij values for zonal pairs. So there is no way such changes can be brought into the picture as per the growth factor method. Clear? These methods neglect the effect of changes in travel pattern by the construction of new facilities and new network. Right? Travel pattern itself might change. So this kind of changes cannot be accounted for in the growth factor method. Right? Please note that all these disadvantages are taken care of in the synthetic model, namely gravity model. We consider all these possibilities. Then present or base year trip distribution matrix must be obtained first for applying these methods, for which large scale origin destination studies with high sample sizes are needed to estimate the zone to zone movements accurately. Another important requirement, your planning expenditure is going to be high in the form of increased requirement for data collection. Your sample size has to be increased and you must collect very accurate data with regard to trip interchanges between zonal pairs. So this is another important disadvantage of growth factor method. This is the first question I posed to you at the beginning of this class. What is the data requirement for growth factor method of trip distribution? We need to have OD matrix for base year condition, which is going to be expensive because of the requirement of large database to develop such matrices if you want to be accurate. Clear? And as I told you, Fraters method and furnace method are still applied for certain specific situations. Specific situations under which growth factor method may be used. And you may recall our discussion with regard to the possible types of trips that might take place in urban area. The most common trip interchanges are between traffic zones within the boundary that we delineate as your study area boundary. Let us say on a typical day that you consider for your study, certain percentage of trips have emanated from outside your study area and ended up in different traffic zones inside your study area. People have travelled from Tiruchirappalli and arrived at Chennai. Chennai is your study area, right. It is one way movement. So, trip origin is not within your study zones, it is elsewhere, but this trip is also going to add to the traffic in your city road network. So, this kind of trip is called external to internal trip. Internal is your study area. Similarly, certain percentage of people might have travelled on your particular day under consideration from Chennai to different places, different other places, Chennai to Delhi, Chennai to Vijayawada, Chennai to Tiruchirappalli, Chennai to some other destination, Bombay and so on. All are trips contributing to the traffic on that particular day, but it is one way movement. Trip origin is in your study area, destination is elsewhere, and this kind of trips are going to be there in the horizon year also, isn't it. How to account for the prediction of this kind of trip distribution in the horizon year? Since you have traffic zones within the study area, we are able to predict the trip production, trip attraction, in turn trip origins and trip destinations for all the zones in your study area. Whereas when the other end of your trip is outside the study area, you cannot treat that as a zone and go into the details of the socio-economic characteristics that influence the number of trip origins, destinations, etc., which is too much, right. So, in such a case you try to manipulate the present day trip interchanges to get the future trip interchanges. That is how the growth factor methods are relevant to deal with internal to external trips and the external to internal trips. Clear? Growth factor methods may be used to estimate trip interchanges involving traffic zones outside the study area, external trips. As calibration of gravity models under such cases would be difficult due to vast differences in travel times. Within urban area, your travel time range could be nearly a minute to, let us say, about 70 minutes. Whereas if you take a travel time between Chennai and Vijayawada, Chennai and New Delhi, it is not going to be comparable. When such vast variation is there, you cannot apply your gravity model, it will not work, okay. Under such cases will be extremely difficult, application of gravity model under such cases will be extremely difficult due to vast differences in travel times of internal to internal trips which are within a range, and internal to external or external to internal trips, and the associated analytical problems. That is how you cannot apply your gravity model to deal with internal to external and external to internal trips. That is where your growth factor methods will be very useful. The growth factor methods may be applied for short term forecasting. This is another situation where growth factor methods can be advantageously made use of. For short term forecasting of trip distribution in urban areas where the zonal growth rates are expected to be marginal and more or less uniform, right. In that case there is no problem and you can go in for application of growth factor method. Let us say for some reason you would like to have some idea about the trip distribution pattern for a time which is about 5 years ahead, and the base year value is known to you. There is no need to worry about gravity model application for such requirements. You can as well do the exercise using growth factor method, right. So these are the two specific situations where still growth factor methods are valid, right. So this completes our discussion on trip distribution analysis. To summarize what we did in this class, we started our discussion with growth factor methods of distribution, and we discussed in detail about two specific methods. The first method that we discussed was Fratter's method of trip distribution, and Fratter's method is an iterative procedure which just manipulates the cell values of the matrix based on the predicted trip origin and trip destinations for the horizon year, isn't it. And it is iterative procedure, and iteration ends when the growth factors become unity or nearly unity in all the cases. Furness method, the second one that we discussed about, this is similar to Fratter's method, but very simple in the analytical procedure because we just scale up the cell values using the growth factors of origins and destinations. In this method also we stop the iteration when the growth factors approach unity. With this we will close for today, and we will continue our discussion in the next class on the new topic, namely route assignment or traffic assignment.